Here in video lecture 7.4, we look at one of the chemical weathering types, carbonation, in the form of its creation of karst landscapes, which we definitely find here in Indiana. Before describing specific landforms created from this chemical weathering type, I'm going to describe the recipe required for it. First off, you have to have a lot of limestone. And so one of the things is limestone's characteristic. It has this mineral calcium carbonate. It's kind of weak. It's very susceptible to chemical weathering. And so one of the things is limestone. We have it all over Indiana. We described that in video lecture 6. But we have certain areas of our state where that limestone is close to the surface. And so one of the characteristics of karst landscapes is limestone, but also limestone is close to the surface. Further, carbonation. I described carbonation in the previous video lecture section, and so you then have to have carbonation. So in Indiana, because we have a good amount of precipitation, we're going to have more likelihood of that rain picking up CO2 in the atmosphere or the soil. And so that's the second key ingredient. Third, it takes a lot of time, and so this is a very, very slow process. Here we have a tombstone that uses limestone. Why would they use limestone? In Indiana, we see these in old cemeteries. Why would they use limestone? It's the rock underneath them. And so if you're going to memorialize someone, you're not going to use a tree, you're not going to use some twigs, you're going to put down a stone. But one of the things this illustrates, though, is chemical weathering. And so this is a cemetery in which people, most of the other people in this area died in the 1850 to 1890 range. So we know that this is about 130 years of chemical weathering that's slowly eaten away at this limestone. And what this does is shows two things. It shows the time it takes for chemical weathering to occur, but it nonetheless also shows chemical weathering and how it slowly eats away at this underlying bedrock, in this case limestone, that's very much exposed at the surface now that we have it sticking out of the ground. In terms of speeding up the whole chemical weathering process and the carbonation process, it requires hot, muggy, humid climates that always have a good amount of humid air. And so if we go to the tropical areas, once again relating it to previous concepts, we can see when you have limestone combined with tropical areas, tropical climates, that's really going to speed up this whole karst process. And so we can see that here. It's hard to fathom, but this entire area was actually all one solid chunk of bedrock. But over time, it's been chemically weathered away so that the only ones that remain are the Chuck Norrises of rock, the resistant rock, the limestone. That will eventually be eaten away, but nonetheless here has been able to survive and withstand chemical weathering. Now let's take that same idea with the tombstone and relate it to our underlying bedrock. And so here we can visualize the carbonic acid being the pink stuff. And so we have cracks in the limestone. How are we going to have cracks? Why are we going to have cracks? Plate tectonics can create cracks once you put push on something or also relieve the stress on something. Also, various heating and cooling back and forth, freeze thaw can also create cracks. And so over time, these cracks, they widen because that carbonic acid slowly eats away and it goes in those joints, those cracks, and slowly widens them over time. Keep in mind it takes a long time for this to occur. This does not happen overnight. These cracks within the underlying limestone, they get bigger over time as that chemical weathering, as that carbonic acid slowly eats away at that calcium carbonate rock, the limestone rock, that's susceptible to that chemical weathering slowly eating carbonation, slowly eating away at that rock. Now let's discuss some specific landforms created from this chemical weathering form. First off, you're going to get a very pitted, bumpy surface. So thinking about a golf ball. A golf ball has all those dimples, very similar to what we would find here in a karst landscape area. Further, it's going to have poor surface drainage. What I mean by that is if we get a ton of rain, what's going to happen is those dimples on that golf ball are going to hold and store the water. So we're not going to get a bunch of creeks running into streams and rivers, and so you don't get that natural river formation that I'll talk about later in this video lecture series. So essentially what happens is those little dimples hold that water. And so one of the things you saw in the previous images, these well-developed underground channels that do a good job of moving precipitation through the underlying bedrock. And one of the things you'll note the result of the water table, how it actually lowers because of that. That was noted on the previous images. One thing I'll talk about in this specific discussion is this area of south central Indiana, Bloomington to Bedford, Medford to Salem, is an area in which you have an abundance of karst topography. Why? This is where you find limestone close to the surface, which once again goes back to something I just mentioned. So here's the one area in which you have limestone that's rather close to the surface, and in many respects exposed at the surface. 4 key landforms created from karst topography are caves and caverns, sinkholes, karst valleys, and disappearing streams, all of which I'm going to talk about right now. Here's the area of south central Indiana where you find karst topography. And so we do have these rivers that come through and dissect this karst topography area. But the key idea here is this is where you have limestone very close to the surface. And so these landforms I'm getting ready to mention, you're going to find them within this circle here. First, caves and caverns, and so this is created from, once again, typically from limestone and carbonation. But the idea here is the water table lowers, and so when the water table lowers, what fills in that crack that was previously water coming through there? Air. And so then when it's exposed, we can then now walk in it. And so if you've ever been caving in Indiana, I guarantee you it's been somewhere in this area here. So this is simply the water table lowering and exposing the caves and the caverns to humans. One of the things you'll note, though, if you do go in one of these caves and caverns, you will come across some water. So that's still the whole process of percolation, rainwater, and all of that, in which you see essentially carbonation in action. Next up are sinkholes. They are circular, funnel-shaped depressions on the surface. And so key to understanding them is karst below the surface. And so you have these underlying cracks in the limestone that get bigger and bigger and bigger over time. Over time, they can't support the weight above it. So essentially what happens is those underground caverns, they collapse, and then above them, the surface collapses and creates these sinkholes and creates these depressions. Thus, the whole idea of a pitted, bumpy surface that looks a lot like a golf ball. This is an image from south central Indiana. I'll come back to this more in the discussion, but here, although you can't tell, I mean, because the whole layer of carpet that we call corn and grass covers these sinkholes, covers this pitted, bumpy surface, and so underneath this, we can just simply tell by looking at this field that there's limestone very close to the surface. So here we see a sinkhole that's full of water, and so this is very characteristic of this area of south central Indiana. And so once again, poor surface drainage. We don't see this all flowing into a river that all flows in eventually to the Gulf of Mexico, all of that. No, we see essentially those dimples, those holes being filled with precipitation, with rainwater, and then of course becoming a lake. Now, when you get several sinkholes all in a line together, what that's going to do is it's going to create an elongated depression, or it's going to create a situation in which you have this karst valley. And so it's a valley, but it's not a valley created because of rivers. It's a valley created from simply depressions all right next to each other that are rather linear, all collapsing, and thus creating a valley. Finally, a disappearing stream or a lost river. Essentially what happens here is a surface stream will essentially go down into a sinkhole, go through the underlying bedrock, go through the cracks, and come out usually as a spring somewhere else. And so essentially the water, the river, it's continued to go downhill. The whole idea, though, went downhill and underground so that you don't see it anymore. So in Indiana and south central Indiana, we've got these disappearing streams, essentially, in which those streams go underwater, then reemerge somewhere else. If you go back and look at the previous image, you can really see the whole idea of a spring and how it lowers the water table, but you can see that lost river idea.